Okay, we have a hypothetical situation in the 13th problem. We have 100 individuals. Everyone contacts everyone else once a day. The probability of infection is 1.2% upon contact of a non-infected with a non-immune infected individual. So the first question, how many individuals would you expect to be infected after 1 day, assuming that there are initially 3 infected and nobody is immune? Hopefully you've stopped and thought about that a bit. Well, let's just consider something. 100 people, everybody, okay, just think you're one of these individuals. You're going to make how many contacts? You're going to make 99 contacts during the day. 100 people each making 99 contacts means that you have 100 times 99 or 9,900 contacts. Now, 1.2% of 9,900 would be over 100 people. But fortunately, not all of these contacts are between non-infected and infected individuals. Think about yourself, if you're one of this group, how many infected individuals are you going to come up in contact with during a day? And, well, take it from there a little bit. Okay, well, hopefully you paused and thought about that. Okay, there are 3 people infected. So you would come in contact with all 3 of them, assuming you're not one of the ones that's infected. So there are 97 people and each makes contact three infected people and 96 not infected. Okay, so how many infections do we expect for the second day? Again, pause and think a little bit, but I'm going to continue. Well, that means there are 97 people each coming in contact with 3 infected people. So the number of contacts between non-infected and infected people is 3 times 97. So I'll say there are 97 times 3 contacts between I standing for infected and N standing for non-infected. Now how many infections are we going to get out of that? Well, 1.2% of those contacts are going to result in infections. So we get 0.012, which is 1.2%, times our 97 times 3. Now 97 is really close to 100. 3 times 97 should be really close to 300. And 0.012 times 300 is 3.6. Of course, 97 is 3% less than 3.6. So I'll say take off 3% of 3.6, and we're going to get about 3.5 infections. What now is the status of our population starting the second day? Well, one of the conditions, and I didn't write it down here, is that this infection lasts for only 1 day, after which the person is immune. So our 3 infected people from the first day are now immune, and nobody dies from this thing. We have 3.5 people infected, and of course, how can you have half a person infected? That really means we have either, our probability is that we have 3 or 4 people infected, maybe fewer, maybe more, but the most probable mean number of infected we would have would be 3.5, which would leave us 93.5, not 93.3. I can kind of change that 3 to 5. You can get away with that. Okay, 93.5 are susceptible. So now we're going to have three categories. We're going to have immune people who've had the infection and recovered, infected people who can infect others, and susceptible people, people who haven't been infected and of course and are not infected. People who haven't been infected. They're susceptible to the infection. So now what's going to happen on the second day? How many infected people are we going to have after the second day, and how many susceptible and how many immune? Should be able to work that out. Now, a better way to have asked the question would be to not ask what are we going to have at the end of the second day. To answer that question, you would want to ask yourself the question, well, what happens on the second day? So if you haven't been able to think that through, try approaching the question as what happens on the second day. Well, many things happen. There are, again, 9,900 contacts between people, but that isn't particularly important. It's important to kind of understand that to give us a context, but what counts is the number of contacts between non-infected people or susceptible people in this case. Before, everybody who was non-infected was assumed to be susceptible. 93.5 those susceptible people, each encountering 3.5 infected people. So we have 93.5 times 3.5 encounters of infected with, I used N for non-infected, but I probably would have been better off to use S for susceptible. So let me change that. So of infected people with susceptible people, that looks a lot like a 5, but I'm not sure there's much I can do about that. Hopefully you understand what that means. So we get 0.012 multiplied by 93.5 multiplied by 3.5, and what's that approximately equal to? Well, 100 times 3.5 would be 350. This is about 7% less than that. 7% of 350 would be about 20. So I'm going to say about 320. And 0.012 times 320 would be about 3.8. And that's going to be 3.8 infections. Are going to occur as a result of these contacts. Now, so where does that leave us? To the third day. You should ponder that. So I find a good piece of chalk. Okay, so for the third day, we now have, well, we have 3 immune, and now the 3.5 who were infected are immune. So now we have 3 plus 3.5 equals 6.5 immune. We have 3.8 infected. Yeah, just wrote that, got to pause. Okay, 3.8 infected, 89.7 susceptible. And we get that easily by adding the 6.5 to 3.8, which gives us the number of immune and infected, and then subtract that from 100 to get the number susceptible. Okay, well, what happens on the third day? Well, be sure to thought through another day. And if my numbers are right and you want to check my arithmetic, we have 89.5 susceptible, 3.8 infected. We multiply those numbers to get the number of contacts between susceptible and infected, and then we multiply that by the 1.2%, and I believe we get 4.1 infected. Now we have 10.3 immune, 85.6 susceptible. So we see the pattern so far is that this infection seems to be progressing. We seem to be getting more and more infected people. We go from 3 to 3.5 to 3.8 and now to 4.1 infected people. Is this going to continue? How long can this continue? Well, it can't continue that long. It can't continue increasing very long because there are only 85 susceptible people left. If we keep getting 4 or more infected people, well, 85 divided by 4 is about 21. It can't go on more than about 21 days, and if the number of infected keeps increasing, it'll be less than that. Let's also think about the fact that the number of susceptible people is decreasing while the number of immune people is increasing. Okay, what is changing more rapidly? The number of immune people, is the number of immune people increasing more quickly than the number of susceptible people is decreasing? As long as it is, then the number of infections is going to continue to climb. However, that isn't going to continue forever, and if you do a couple of cursory calculations, 3 out of 4.1 is about, I'm sorry, what am I saying? 3 out of 4.1. 0.3 out of 4.1 is about 7%. Okay, from 89 down to 85 is about 5%. So right now it looks like the number of new infections is increasing faster than the number of susceptibles is decreasing. So we do expect the number of infections to continue to increase for a little while until the number of susceptibles drops far enough and the number of infected starts to level off and even decrease. Now, my calculations are very approximate and they're actually off. This 4.1 should actually be 4.25. These numbers up here aren't all exactly correct, so you should recalculate them. Now I'm going to give you some correct numbers. Okay, now I'm just reporting some numbers. I didn't calculate these in my head or by hand. I used machinery to do this. The numbers of infected after 5, 10, 15, 20, 25, and 30 days climbed to 4.37, and it turns out on day 5 that's as high as it goes. After 10 days, it's down to 2.22. After 15 days, 0.47. And it drops off to less than half after 20 days and 25 and 30, which means that most likely sometime shortly after the 15th day or maybe on the 15th day, we expect no new infections and the disease pretty much dies out somewhere around the 15th day. And the numbers of immune, if we extend this, go from 14.7 to 33.4 to 40.2. And then if we continue the process even after it becomes very likely that the whole thing has died out, but if we assume we can have tiny fractions of infections with tiny probabilities, the number of immune pretty much stabilizes. It only changes from 41.55 to 41.82. That's by 0.27 infections over a whole 10-day stretch. So these numbers appear to be converging. These numbers appear to be converging to 0. And of course, if the number of infected converges to 0, the number of immune is going to have to converge to some value. Because if you don't have any more infections, you don't get any more immune people. Now, it might be kind of interesting to look at these sequences of numbers just on their own to see what they tell us, but this pretty much sums up what we get from this infection model.